Let's finish this example. We were right near the end. Just as a recap, in case it's been a while since you've seen the last video, we use the indefinite integral and u substitution. Since obviously the chain rule was used here to find the derivative, we have to use u substitution to undo that chain rule. We find the antiderivative function, substitute back in the original variable, and pick up the original limits of integration. And now we show that we are going to do fundamental theorem here. So we have 1/8. We plug in our upper limit of integration, and then minus 1/8, and we plug in our lower limit of integration. So there's fundamental theorem. Again, if this were free response, we would be done here. So we have 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. 2 to the 4th is 16. So we have 16/8 minus 1/8. Multiple choice would look like 15/8. That is the exact area trapped in the plane in between this function and the horizontal axis over the interval from 0 to 1. Now, one thing that I do want to say on fundamental theorem, I know I just gave it to you and we've taken off and done a couple of examples, and I didn't really prove to you why it's true. I meant to say this in the last video, so I'll insert it here. In the past, up until this year as a matter of fact, I've always shown not a rigorous proof, but a visual proof using area in the plane, and I've illustrated why fundamental theorem of calculus, the antiderivative at the upper limit minus the antiderivative at the lower limit, will always give us exact area. But what I have found every single solitary year that I have done that is that it just confuses the fire out of students, and in the end I've been told that they wish I had just given them the fundamental theorem and started using it and not confuse the issue. You'll never be asked to determine why it's true. You don't need to know why it's true. But for the students that would like to know why it's true and see a rigorous proof, then I suggest just Google fundamental theorem of calculus and proof. And it will, you'll find several places where they'll actually go through the proof of why fundamental theorem is always true. But I'm not going to take time to do it. I'm going to drop that this year because I really don't think it's a good use of my time. So let's work another example. So we have the definite integral from 1 up to 4, and our function is the quantity t minus 4 divided by the square root of t. Well, I really don't see anything being operated on here. So again, the first thing that I'm going to do is I'm on the hunt for my antiderivative. And I don't see u substitution. I don't see any technique here. So just as we always did and just as we've done in the past on our indefinite integrals, we may need to use some algebra. Or if this, if trig was here, maybe we could use a trig substitution. Or don't forget that there's a lot of mathematics that you know where you could turn this into an antiderivative that you could actually take. Because remember, integrals, definite or indefinite, do not break up over the division sign. So don't give the definite integral properties that it doesn't have. So what I'm going to do is I'm going to work inside on the integrand here, and I'm going to realize that I only have one term in my denominator. So that's going to be a common denominator for each term in the numerator. So there is a way that I could hopefully change the way that my integrand looks without changing its value. Now this is t to the 1 over t to the 1/2. Remember, it is the upper power minus the lower power. So that actually cleans up to t to the 1 minus 1/2, or t to the positive 1/2. I really can't clean this up much, but what I can do is turn it into a power rule for integrals problem. So now I can find that antiderivative. And so the antiderivative of this is 1 over n plus 1, remember that, times t to the n plus 1. And this is going to be minus 4 times 1 over n plus 1 t to the n plus 1. And now I'm going to, clean this up a little bit before I take off and actually do fundamental theorem. But I am working on a definite integral, so I don't put a plus c out here. Okay, maybe we need to put that in our notes. Never put plus c on a definite integral. If you have limits of integration, you have a definite integral. So when we have a definite integral, we don't put plus c, because this is telling us to do something different than the indefinite integral is telling us to do. This is instructions for find the antiderivative function. And the antiderivative function could have had a constant on it that differentiated to 0 when we took the derivative. That's the instructions that the indefinite integral is giving us. The instructions the definite integral is giving us is use the fundamental theorem to find the area. Find the area. Okay, so two different sets of instructions, even though our work looks a whole lot the same on both of them. So let's clean this up, and then we can actually do fundamental theorem. So this is 1 over 3 halves. 1 over 3 halves cleans up to 2/3. T to the 1/2 plus 1 is 3 halves, and then minus, just working on this coefficient here, that is 1 over negative 1/2 plus 1. So that's 1 over positive 1/2. So this cleans up to a positive 2. And negative 4 times positive 2 is 8. T to the positive 1/2. And now we're actually ready to plug in our upper limit and our lower limit. So if I have more than one term in my antiderivative, I usually like to include parentheses or brackets or something that will help me keep the antiderivative at the upper limit separate from the antiderivative at the lower limit. So I'm going to plug in my upper limit into the entire antiderivative function, the whole thing. There is my entire antiderivative function evaluated at the upper limit. And now that's minus the entire antiderivative function evaluated at the lower limit. And this separator here, this, whether it's a parentheses or a bracket or braces, whatever you use, is really important on the second part of fundamental theorem, so that you remember to distribute that negative over all the different pieces of your antiderivative function. So your work needs to look like this. So we have, let's see, 4 to the 3 halves. Let's come over here to the side. 4 to the 3 halves is equivalent to the square root of 4 cubed. And 4 cubed is 64. So just this right here is 8. So I have 2/3 times 8, so that cleans up to 16/3. And I'm going to copy down all of my separators here. The square root of 4 is 2, and 2 times 8 is 16. 1 to the 3 halves is 1, so this is 2/3, and 1 to the square root of 1 is 1, so minus 8. Again, if this was a free response question, I would stop at this step right here. I wouldn't attempt to clean it up or take my valuable time to clean it up. So let's get our terms together. We have 16/3 minus 2/3, and then we have a negative 16 and a positive 8. So let's clean that up a little bit. We have 14/3 minus 8. If we wanted just one term here, that's 14/3 minus 24/3, so that cleans up to a negative 10/3. And don't be troubled by a negative value. Remember, area in the plane can accumulate to a negative value, so not a problem at all. So don't forget that we already have a lot of techniques, and U substitution isn't the only one, to be able to evaluate these definite integrals. Okay, here's another U substitution example. We're going to pick whatever's being operated on as the first natural choice for U. We're going to find our differential, which is 2x dx. We can clearly see that we're off by a factor of 2. When we use u substitution with the definite integral, we are then using the indefinite integral to find our antiderivative. So I'm going to pop my constant out front. The antiderivative of that function is 1/3 u cubed. This is an indefinite integral, so I have to put a plus c there. This cleans up to 1/6 u cubed plus c. Now I have identified my antiderivative function. I'm going to come back here. I'm going to substitute back into the original variable, and I'm going to apply fundamental theorem. So this is 1/6 1 squared plus 2 quantity cubed minus 1/6 0 squared plus 2 quantity cubed. So there's fundamental theorem. So this is 1/6 times 3 cubed minus 1/6 times 2 cubed. I'm not going to take any more time to simplify that anymore. You guys know what 3 cubed is and 2 cubed is. All right, so I want to make a point. This is why we're doing another example like this. I want to make a point that we are using the indefinite integral in u to find our antiderivative function. There is an alternate way that this problem can be solved, and we can solve it in terms of u. But I'm going to have a cautionary tale right at the end. But we're going to rework this problem using this information and using this antiderivative function. So if we were given this problem, we would rewrite it in terms of u. But let's say we wanted a definite integral in terms of u, which we could definitely do, and then we wouldn't have to back substitute in terms of our original variable. Okay? Now here's something that is very, very important to what I'm fixing to tell you. I want to highlight the fact that u does not equal x. U equals x squared plus 2. If u equaled x, then this would just simply have a lower limit of 0 and an upper limit of 1. But since u does not equal x, since u equals x squared plus 2, then when x equals 0, which is our lower limit of integration, u of 0, I'm plugging 0 in here for x, u of 0 is 2. So as far as u is concerned, the lower limit of integration is 2, not 0, because here's the relationship between u and x, not this. All right? When x equals 1, which is the upper limit of integration, plugging 1 into the u relationship gives me 1 squared plus 2, and so that gives me 3. All right, so the upper limit as far as u is concerned is 3. Now, we don't have to back substitute. We have a definite integral here. We can find the antiderivative function just like we did on the indefinite integral right here. And it would look like this. And then we would use fundamental theorem using those u limits. So we would get 1/6 3 cubed minus 1/6 2 cubed. Does that look familiar? It should. Just because I found new u limits of integration instead of x limits of integration doesn't mean that I changed the area that's actually trapped in the plane. So this is an alternate way if you want to find new u limits of integration where you don't have to back substitute in terms of x. We'll talk a little more about this in the next video.